Ever have your phone just go completely haywire? Or like your GPS, it just leads you on this crazy wild goose chase. Oh,
Okay.
well, imagine that, but like on a global scale.
Oh, wow.
That's
And just like a boiling pot sends steam into the air, the sun constantly spews out a stream of these charged particles. That's what we call the solar wind.
so it's like a constant solar breeze.
Yeah,
But instead of air, it's made of these tiny, super energized particles.
exactly. And sometimes this breeze turns into a full-blown hurricane.
Oh, wow.
Those are the solar storms we're trying to predict. They happen when the sun releases massive bursts of energy and plasma called coronal mass ejections, or CMEs.
Okay, so these CMEs, these are what can mess with our tech here on Earth.
That's right. When these CMEs hit Earth, they can cause all sorts of problems, from disrupting satellite communications to knocking out power grids.
So how does this new model help us predict these, I guess, solar hurricanes? Did this grad student, Thomas Dew, did he find some secret, like, solar weather forecast?
Well, he didn't exactly consult a crystal ball, but he did come up with a brilliant way to predict how these CMEs create something called shock waves, and how those shock waves accelerate particles to incredibly high speeds. These particles are the real troublemakers when it comes to solar storms.
Hold on, shockwaves. Are we talking like sonic booms in space?
Kind of. Imagine dropping a pebble in a pond. You see those ripples spreading outward?
Yeah.
That's similar to what happens when a CME explodes from the sun. It creates a shock wave that ripples through space.
Okay, so the CME is like the pebble and the shockwave is the ripple.
Uh-huh.
But how do those ripples cause trouble all the way here on Earth?
That's where the particle acceleration comes in. Think of these shock waves like giant cosmic surf waves.
Okay.
And the particles from the sun are like tiny surfers catching those waves. As the particles ride the wave, they gain incredible amounts of energy and speed. Some of them even escape the shock wave altogether and shoot off into space.
Whoa, so it's like the sun is launching these tiny supercharged bullets into space.
That's a pretty good analogy. And the problem is, some of those bullets are aimed right at Earth. What Dew's model does is predict how many particles escape at different energy levels, which is something older models couldn't do well.
So he's figured out how to, like, map out the trajectory of these solar bullets? That seems incredibly complex.
It is, but that's what makes his work so groundbreaking.
Right.
And the really amazing thing is, they were able to test this model using data from a real solar storm.
Wait, the sun conveniently threw a solar storm while they were working on this? Lucky timing.
You could say that. In September 2022, there was a massive CME, and NASA's Parker Solar Probe was in a perfect position to collect data.
Oh, wow.
This probe is no ordinary spacecraft. It's designed to get closer to the sun than anything we've ever sent before. Imagine the Earth and sun were a meter apart. This probe was just 7 centimeters from the sun.
Wow, that's practically touching the sun.
I know.
It must have had front row seats to this solar storm.
It did. And when they compared the data from the probe to the predictions from Dew's model, they were almost a perfect match. It was the first time we'd been able to test these predictions for these types of shock waves so close to the sun.
So this grad student, Thomas Dew, has basically revolutionized how we understand and predict these solar storms. That's incredible.
Yeah.
This means we can now predict solar storms with more accuracy than ever, which could be a game changer for protecting our satellites and power grids. Plus, this knowledge could help us understand similar processes happening in other parts of the universe.
It's pretty remarkable.
Yeah.
And it raises so many exciting possibilities. We're not just talking about space weather forecasts here, but potentially understanding fundamental processes that happen all over the cosmos.
Okay, my mind is officially blown.
Yeah.
This is way bigger than I initially thought.
I know, right?
But before we dive into all that, I need a minute to process. You mentioned earlier that this research could have implications for other areas of space research. What exactly do you mean by that?
Well, that's where things get even more interesting.
All right, my brain is somewhat reassembled after that last bit of information. So you were saying this research could have implications for other areas of space research. Where do we even begin to unpack that?
Well, for starters, this model isn't just about predicting solar storms. It's a major step forward in understanding how particles behave in extreme environments.
Right.
And those kinds of environments exist all over the universe, not just near the sun.
Okay, so we're talking about places where things get really intense, like supernova explosions intense.
Exactly. Remember those super high energy particles we talked about earlier?
Yeah.
The ones called cosmic rays?
Yeah, the ones that come from exploded stars and other crazy cosmic
Right.
events.
Well, those particles get accelerated to incredible speeds by shock waves, just like the ones created by CMEs. So, by studying how particles behave in the solar wind, we're actually learning about processes that happen on a much grander scale throughout the universe.
So the sun is like a giant laboratory for studying cosmic particle accelerator.
You could say that. And the insights we gain here can be applied to all sorts of astrophysical puzzles.
Like what? Give me an example.
Well, one area where this research could have a big impact is in the study of black holes.
Black holes, now we're really going deep. Those things are mind-boggling.
They are. And one of the big mysteries surrounding black holes is how they accelerate particles to nearly the speed of light. We see these incredibly powerful jets of material shooting out from black holes, but we're still trying to understand exactly how that happens.
And you're saying this new model, the one that predicts solar storms, could help us understand black hole jets. How is that even possible?
It all comes down to the fundamental physics of particle acceleration. Even though the environments around black holes are vastly different from the solar wind, the basic principles are thought to be similar. It's like learning to ride a bike on a flat surface and then using those same skills to navigate a mountain trail.
Right.
The terrain is different, but the core principles are the same.
So, by studying the sun, which is relatively close and, well, let's just say a bit less intimidating than a black hole, we can gain insights into these incredibly powerful and distant objects.
Exactly. It's a fascinating example of how science can connect seemingly unrelated phenomena. And that's not all. This research could also have implications for understanding the environments around other stars, which could help us in the search for planets beyond our solar system.
Wait, so this research that started with trying to protect our satellites could help us find alien worlds. That's amazing.
It is. And it all starts with understanding the basic building blocks of the universe, things like plasma, particles, and shock waves.
Okay, that makes sense. But you know what else blows my mind? The fact that this breakthrough came from a grad student. It's like, what have I been doing with my life?
It really is inspiring. It shows that sometimes the biggest discoveries come from asking the right questions and having the determination to find the answers.
Yeah. It's a good reminder that there's still so much we don't know about the universe, and that anyone, even a grad student, can make a groundbreaking discovery. But let's not get too lost in the cosmic wonder here. We were talking about practical applications. You mentioned that this research could help us understand things here on Earth too, right?
That's right. Remember how I said that the principles of particle acceleration are relevant to many different fields?
Yeah.
Well, one area where this research could have a real-world impact is in the development of fusion energy.
Fusion energy. Isn't that the holy grail of clean energy? The kind that could power our cities without producing any greenhouse gases.
Exactly. And it all comes down to controlling plasma.
Okay.
You see, fusion reactions, the same reactions that power the sun, happen when you heat plasma to incredibly high temperatures and pressures, forcing atoms to fuse together.
So it's like recreating a tiny sun here on Earth.
In a way, yes, but it's incredibly difficult to control plasma at those extreme temperatures. That's where our understanding of particle behavior comes in.
So you're saying that the insights from this solar storm research could help us design more efficient and stable fusion reactors?
Potentially, yes. By learning how particles behave in the solar wind, we can gain a better understanding of how to control and confine plasma in a fusion reactor.
Wow, that would be huge. If we could crack the code of fusion energy, it would revolutionize how we power our world.
It would be a game changer. And it all stems from fundamental research into the nature of the universe.
That's the thing about science, isn't it? It's all interconnected. What starts as a quest to understand something seemingly distant, like solar storms, can end up having a profound impact on our lives here on Earth.
It really is remarkable. And who knows what other unexpected applications might arise from this research in the future. But there's one more area where this research could have a huge impact, and that's in the prediction of earthquakes.
Okay, earthquakes. That's a big one. We've been trying to predict those for centuries with very limited success. What makes you think this solar storm research could help? Okay, earthquakes. That's a big one. We've been trying to predict those for centuries with very limited success. What makes you think this solar storm research could help?
Well, it's not that solar storms directly cause earthquakes. That's not what we're saying.
Right.
But the sophisticated modeling techniques that Thomas Doan developed to predict particle behavior in the solar wind, those same techniques could potentially be applied to understanding the complex forces at play within the Earth's crust.
So instead of predicting when the sun is going to erupt, we're talking about predicting when the Earth itself is going to shake things up.
Precisely. Earthquakes are caused by the buildup of stress along fault lines in the Earth's crust.
Right.
And while we can't see these forces directly, we can use sensors to collect data on things like ground movement, changes in pressure, and even tiny variations in Earth's magnetic field.
And you're thinking we could apply Doan's model to this kind of data?
Exactly.
Yeah.
His model is all about understanding how energy builds up and is released, and how that energy affects the behavior of particles. That's relevant to earthquakes, too. If we can build a model that accurately simulates the complex interactions of forces within the Earth's crust, we might be able to get a better idea of where and when those stresses are likely to reach a breaking point.
So we're talking about going from earthquake detection to earthquake prediction. That would be a paradigm shift. Imagine being able to issue early warnings that give people time to evacuate vulnerable areas before a major earthquake hits. It could save countless lives.
It's a powerful possibility, and it's just one example of how the knowledge gained from this solar storm research could have far-reaching implications.
Okay, I'm starting to see a pattern here. First, we were talking about protecting our satellites and power grids.
Yeah.
Then we jumped to black holes and alien planets. Now we're on to earthquake prediction. It's like this research is opening up a whole new universe of possibilities. What other seemingly impossible to predict things might become, well, predictable?
That's the exciting part, isn't it? This research, while focused on solar storms, opens up possibilities in so many other areas. Let's take, for instance, the prediction of volcanic eruptions.
Okay, yeah, volcanoes, those are pretty unpredictable too.
Exactly. But, similar to earthquakes, they are caused by the buildup of pressure and magma beneath the Earth's surface. The same kind of sophisticated modeling that could help us predict earthquakes could also be applied to volcanoes, potentially giving us a heads up before a major eruption.
So instead of just reacting to natural disasters, we could be proactively preparing for them. That's a game changer.
Absolutely. And let's not forget about climate modeling. We're constantly refining our understanding of how Earth's climate system works. More accurate models, built using the same principles that Doe used for his solar storm model, could help us better predict extreme weather events, sea level rise, and other climate-related impacts, allowing us to make more informed decisions about mitigation and adaptation.
So it's like we're gaining a deeper understanding of the interconnectedness of everything, from the sun to the Earth's core to the very climate we depend on. And it all started with a grad student asking some really good questions about solar storms.
It just goes to show that the pursuit of knowledge can lead us down unexpected and incredibly rewarding paths. Who knows what other mysteries will unravel in the years to come?
It's both humbling and incredibly inspiring. So for anyone listening, keep your eyes on the skies and your minds open to the possibilities. This is just the beginning.
Well said. Keep exploring, keep questioning, and keep that sense of wonder alive.
And that's a wrap on our deep dive into the fascinating world of solar storms, the groundbreaking research that's changing how we understand them, and the amazing possibilities this opens up for the future. Don't forget to check out the source article for more details and to keep up with the latest discoveries in this exciting field. Until next time, keep exploring.